So in this lecture, I'm going to introduce concept of series, then do some questions involving series, adding series. So series. So a series is a sum of terms of a sequence. So e.g., that is, we obtain a series from the sequence as A1, A2, A3, A4, etc. plus AN. So when we add the terms of a sequence, then we obtain a series. So we denote I'll call this one 1. The series 1 as or simply write it in this form. So we'll be interested now in finding how can we be able to get a sum of a series which has an infinite terms. So a definition. Given a series which is A1, A2, A3, let Sn denote its nth partial sum that's to say Sn equals to summation from I1 to n. So we are stopping at the nth term. So up to n of ai given by a1 plus a2 plus a3 up to plus an. So if the sequence is convergent, and the limit as n approaches infinity of Sn equals to S then the series is called convergent, and we write it as A1 plus A2 plus A3 plus AN equals to S, or simply summation n from 1 to infinity of AN equals to S. The number S is called the sum of the series otherwise the series is called divergent. Thus we write to mean so. Notice that this is what you have. So let's do some examples. Find S for the geometric sequence So therefore, remember for this geometric sequence from our high school knowledge, A is called the first term, R is called common ratio. So this is how we do this. So if R equals to 1, then Sn will be given by A plus A plus A plus A, which is Na, which approaches plus or minus infinity. Now, since limit as n approaches infinity of Sn does not exist, the geometric sequence series diverges geometric sequence, not geometric series. The geometric series, not geometric sequence. Diverges in this case. So let's consider another case for R. So let's consider if R is not 1, we have so let's write Sn as A plus AR plus AR squared plus AR cubed plus ARn minus 1. And then let's multiply this by R so that we get Rsn will be given by AR plus AR squared plus AR cubed plus AR power 4 plus AR power n minus 1 plus AR power n. So if we call this one equation 1, call this one equation 2, we can get the difference between these two equations. So that we'll have Sn minus Rsn. Consider in this case when you subtract, this and this cancels, this and this cancels, this and this cancels. This one also has what to cancel here. This also cancels here. All these ones cancels to all these terms here. So we remain with this A and then AR power n. So that will give us A minus A R raised power n. Now from this one, we can have this one minus R Sn equals to A into 1 minus R power n. So making Sn the subject, we have A into 1 minus R power n divided by 1 minus R. So therefore now, if R lies between -1 and 1, so we know that R power n approaches 0 as n approaches infinity. This result we have shown it before. So we have limit as n approaches infinity of Sn the same as limit as n approaches infinity of a1 minus r power n divided by 1 minus r, which will be a over 1 minus r, because this part will be 0, minus, so just now open, so we have two terms, minus a over 1 minus r limit as n approaches infinity of r raised power n. So this will give us, this part here will be 0. Be 0 because this limit gives us 0. So therefore, limit as n approaches infinity of Sn, which is S, is given by a over 1 minus r. So don't forget this. So we can say that thus when absolute value of r is strictly less than 1, the geometric series is convergent and its sum is a over 1 minus r. If r is less than or equals to -1, or r is greater than 1, the sequence is divergent as we have seen it before. And so the geometric series limit as n approaches infinity does not exist. So therefore, the geometric series diverges in these cases. So the only case where the geometric series converges is when r is strictly between -1 and 1. So therefore now, as a summary, we can just say the geometric series is convergent if the absolute value of r is strictly less than 1 and its sum is So don't forget this. So if absolute value of R is greater than or equals to 1, the geometric series is divergent. Now we are mature to do some examples now. So find the sum of the geometric series 5 minus 10 over 3 plus 20 over 9 minus 40 over 27 plus other several terms. So the thing is just to know what R is and what A is. Then you put into the formula. So solution, A is 5, R is minus 10 over 3 divided by 5, which is the same as minus, not really 5, then which is the same as 20 over 9 over minus 10 over 3, which is the same as minus 40 over 27 divided by 20 over 9. When you work out this one, you should get your R to be negative 2 over 3. Yeah. So then now S will be given by A over 1 minus R is 5 over 1 minus 2 over 3, which will be given by 5 over 3, which is 3. So remember, we were lucky to use this formula because this R, its absolute value is less than 1. Then number 2, another example is the series convergent or divergent. So solution to this one, you realize that summation n from 1 to infinity of 2 power n to power 2n 3 raised by 1 minus n is the same as summation n from 1 to infinity of 4 power n over 3 n minus 1. Which is the same thing as summation n from 1 to infinity 4 times 4 into 3 raised to power n minus 1. So we recognize that this series is a geometric series with A as 4 and R as 4 over 3. Now, since R is greater than 1, then the series diverges. So it's a divergent series. A 3, write (2.317) recurring or only recurring for 1 and 7 alone. So the bar is just 1 7 1 7 1 7 1 7 etc. as a ratio of integers. So solution two point 317 17 17 etc. the same as 2.3 plus 17 over 10 power 3 plus 17 over 10 power 5 plus 17 over 10 power 7 plus other terms. So then you say after the first term, we have a geometric series with A 17 over 10 power 3 and R 1 over 10 power 2. So therefore, 2.317 recurring is the same as 2.3 plus 17 over 10 power 3 divided by 1 minus 1 over 10 square. So remember R absolute is less than 1, so that's why we are using this. So therefore, we'll have the same as 2.3 plus 17 over 1000 divided by 99 over 100 will be 23 over 10 plus 17 990, which is 495. That's what we have. Number 4, find the sum of the series where x is less than 1. So solution for this one, where this n is starting, is also very key. So solution, notice that this series starts with n equals to 0, and so the first term is x raised to power 0, which is 1. So thus, summation n from 0 to infinity of x power n will be 1 plus x squared plus x cubed plus x power 4 plus other terms. Then you say, since this is a geometric sequence, with series, not sequence, geometric series, with a equals to 1, r 1 over x. Now r is x, not 1 over x. And since it converges, and thus one over 1 minus x. So this becomes the sum of that series. And then next thing you say, show that. Another example, number 4. The series is convergent and find its sum. So solution, note that this is not a geometric sequence, geometric series. So we go back to the definition of a convergent series, and compute the partial sums. So we have Sn equals to summation I from 1 to n then we can simplify this expression. If we use partial fractions, so you know that 1 over I into I plus 1, if you do the partial fraction decomposition, you should get this. So therefore, Sn, which is summation 1 to n, one over I into I plus 1 equals to summation 1 over I minus 1 over I plus 1. So which will be 1 minus a half plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4, 1 over n minus 1 over n plus 1, which is the same as 1 minus a half plus a half minus a third plus a third minus a quarter minus 1 over n plus 1 over n minus 1 over n plus 1. So you see that some terms will cancel here. This and this, this and this. We are sure that we'll get a positive here, this and this. So therefore we remain with 1 minus, and then limit as n approaches infinity of Sn equals to limit as n approaches infinity 1 minus 1 over n plus 1. And if you work it out, you get 1. So therefore, the given series is convergent and its sum is 1. So that's what we have. Next example. Show that the harmonic series is divergent. Solution for this. So S1 is 1. S2 will be 1 plus a half. S4 will be 1 plus a half plus a third plus 1 over 4, which is greater than 1 plus a half plus a quarter plus a quarter which is 1 plus 2 over 2. S8 is 1 plus a half plus a third plus a quarter plus 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8, which is greater than 1 plus a half plus a quarter plus a quarter plus 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8. This is the same as 1 plus a half plus a half plus a half, which is 1 plus 3 over 2. S16, the same as 1 plus a half plus a third plus a quarter plus 1 over 5 plus 1 over 8 plus 1 over 9 plus 1 over 16. So this is greater than 1 plus a half plus a quarter plus a quarter plus 1 over 8 plus 1 over 8 plus 1 over 16 plus 1 over 16 which is equals to 1 plus a half plus a half plus a half plus a half, which is 1 plus 4 over 2. Similarly, S32 is greater than 1 plus 5 over 2. S64 is greater than 1 plus 6 over 2. And in general, S2 raised power n is greater than 1 plus n over 2. This shows that S2 raised power n approaches infinity as n approaches infinity, and so Sn is divergent. So therefore, the harmonic series diverges. So that's the conclusion. So just another theorem here. if the series then limit as n approaches infinity of an equals to 0. There's a small test for divergence here. Test for divergence. If limit as n approaches infinity of an does not exist, or limit as n approaches infinity of an is not equals to 0, then the series is divergent. So let's do some examples. Show that the series diverges. So solution for this, limit as n approaches infinity of an will be limit as n approaches infinity of n squared over 5, which is the same as limit as n approaches infinity of n squared over n squared 5n squared over n squared, which is limit as n approaches infinity 1 over 5 plus 4 over n squared. And then that one will give us limit as n approaches so this node 0. So therefore the series diverges by the test for divergence. NB if we find limit as n approaches infinity of an is not equals to 0, we know that the series is divergent. if we find that limit as n approaches infinity of n equals to 0, we know nothing about the convergence or divergence of so then also remember that another point, if limit n approaches infinity of n equals to 0, we cannot conclude that and then next point, if we find that the series we find that the limit as n approaches infinity of n is 0, the series might converge or it might diverge. Theorem: if an and bn are convergent series, then so are the series where c is a constant the first one. Then 3, so example on this. find the sum of the series So solution for this so say that is geometric and not really and with a as 1, r as a half. So summation of 1 over 2 power n is a half over 1 minus a half, which is 1. And then we have seen that this worked earlier. So therefore, summation n from 1 to infinity of 3 over n into n plus 1 plus 1 over 2 power n will be 3 summation plus summation which will be 3 times 1 plus 1, which is 4. So therefore, the solution there is 4. I guess a last NB, a finite number of terms cannot affect the convergence of a series. For instance, suppose is convergent, since half plus 2 over 9 it follows that the entire series is convergent. Similarly, if it is known converges, then the full series summation n from 1 to infinity is also convergent. Have a good day.